All right, hello and welcome everyone back to our last lecture of this MoCaO lecture series. Today I'm very happy to announce Bruno Lourenco as our external speaker. So Bruno got his PhD in mathematical and computer science from the Tokyo Institute of Technology in 2016. Afterwards, he worked as an assistant professor at Seikei University and the University of Tokyo, and he's currently an associate professor at the Institute of Statistical Mathematics in Japan. Okay, so whenever you're ready, take it away, Bruno. He's talking about facial reduction and applications.
Thank you very much for the introduction, and thank you very much for having me in this series of lectures. So today I want to talk a bit about facial reduction, and I think my job now is significantly easier because of the past talks. So maybe I can go to more or less directly to the topic. So the kind of problem I'm interested in covering this is the conic linear program. I think Vera has talked about this already, and in yesterday's talk by Isabel, there was also problems related to optimizing a linear function over a convex body. So here, with the kind of problem we consider, is the problem of minimizing some linear function subject to a conic constraint. So here K is a closed convex cone, and affine constraints. So some linear equations of the form AX equal B, where A is a linear map and B is a vector of appropriate dimension. And one thing I like to recall is that if we specialize our cone K to be the non-negative orthant, then we obtain linear programming. And if we specialize our cone K to be the cone of positive semi-definite matrices, then we have what's known as semi-definite programming. Now, before I continue further, I wanted to give some motivation of why thinking about conic linear programming. I think there are several arguments that one can make, but for me, one that I find particularly persuasive is this following fact. So if we are in agreement that convex optimization is important, then you should be forced to agree that conic linear programming is at least equally as important, because in a very important sense, convex optimization and conic linear programming, they are equivalent in a sense. So what I mean by that is that if you start with an arbitrary convex optimization problem, so here f is a convex function, the f is a convex function, this is a convex set. There are a few tricks we can do to convert this into a conic linear program. So first we add one extra variable, this t here, and instead of minimizing fx, we minimize t, but we add the constraint that fx is less or equal than t. Now, these two problems are equivalent. So in the sense that if you obtain either the optimal value or the optimal solution to this problem, you can also obtain the optimal solution or the optimal value for this problem. Now, if you continue further, we can define this set C2, which is just the feasible region of this problem. So this is the set of xt such that x belongs to this C and fx is less or equal than t. So in a sense, this is just the epigraph of f intersected with the Cartesian product between C and R. And now we can construct a convex cone in this space. Here I'm assuming that C is contained in some Euclidean space E. And this will be the cone generated by this. So this will be this set here. So it's the non-negative elements of, sorry, it will be the non-negative multiples of elements of this form, where xt belongs to C2. Now, if we use this cone here, we can reformulate this problem as a conic linear problem in this lifted space. So if we have agreed that these two problems, this problem and this problem, are equivalent, it is not that complicated to see that it should also be equivalent to this one, where we ask xt, where we introduce an extra variable alpha, and we ask xt alpha to be in k, but at the same time we force alpha to be equal to 1. So if alpha is equal to 1, so we are exactly in the slice of the cone that corresponds to this. So for alpha equal to 1, we have that xt1 belongs to k if and only if xt belongs to C2. So we are in the feasible region of this. And conversely, if we have a feasible solution to this problem, we can just append an 1 and get a solution to this conic linear problem. So now this is a conic linear problem because the objective function is linear. We have a linear equality constraint and a conic constraint. So in principle, of course, this cone may be complicated, but in principle, everything that's convex optimization can be captured by conic programming. Now, I'm not saying you should always do this transformation because as a matter of efficiency, it may be the case that solving this formulation directly may be faster depending on the algorithm. But in terms of expressive power, conic linear programming is at least as expressive as general convex optimization. But the philosophy behind conic linear programming is that you try to make solving problems over certain families of cones as efficient as possible, and then you try to convert those problems into this form. So for example, if you have ever used CVXPy, for example, this is what's happening behind the scene. So you feed to CVXPy a convex optimization problem, and behind the scenes, it finds a conic linear programming formulation to send it to some solver. So for me, I think that is one good reason to focus on conic optimization. So at this point, I'd like to ask: are there any questions? Should I? Is everything okay? Good. Okay, so let me continue a bit more. Now, conic optimization problems, they come in primal and dual pairs. So we have a primal problem that is typically but not always a minimization problem, and a dual problem that's typically but not always a maximization problem. And one very important question is to understand when the optimal value of these two problems are the same. So you always get for free a result known as weak duality. So it always happens that if you define the prime and dual problems in this way, it always happens that the primal optimal value is greater or equal than the dual optimal value. This is known as weak duality. However, in contrast to linear programming, in order to have strong duality, in order for the prime optimal value and the dual optimal value to coincide, this is something you do not get for free. You typically need to impose some condition. So we have two different versions of the strong duality theorem, a primal and a dual version. So the primal one says that if you look at the primal problem and it has a relative interior feasible solution, so some x that satisfies the linear constraints but is in the relative interior of the cone, then this ensures that the optimal values are equal, and D has an optimal, and the dual problem has an optimal solution if the prime optimal value is finite. And we also have a dual version of this. So if D has a relative interior solution, so some y such that C minus A star y belongs to the relative interior of the dual cone, then this ensures the equality of the optimal values and that the primal problem has an optimal solution. Now, these kind of conditions are always like this. You assume something on the primal side, and then you get an optimal solution at the other side, provided that the optimal value is finite. And yesterday, in Isabel's talk, I think she talked about how you can use duality of convex bodies to convince yourself that some point that you have is indeed an optimal solution. And here, of course, we have a very similar thing. So if the pair of problems that you have at hand satisfy this kind of regularity conditions, latest condition, you can use an optimal solution of the primal problem to prove that an optimal solution to the dual problem is indeed optimal and vice versa, because of these sufficient and necessary conditions. So if you have a primal and dual problem in this way, a sufficient condition for a pair of solutions to be optimal is first that at the primal side we have feasibility, at the dual side we have feasibility, and we have something known as complementary slackness. So this is the same thing as saying that these solutions afford zero duality gap. So essentially I'm picking the inner product between this and X star, and if I open up a bit, this is essentially giving the difference between optimal values. So if I'm given some X star and I want to prove to you that this X star is optimal to P, one way I can do it is to exhibit one Y star for which these conditions are satisfied. And conversely, if I am interested in solving the dual problem and I have some solution and I want to convince others that this is indeed the optimal solution, one way I could deal with this is to present some X star satisfying these conditions. Now, this is a sufficient condition for getting optimality, but this is not necessary always. However, if we are under these two sets of conditions, if we are under primal and dual latest condition, these conditions above are necessary too. So they become an if and only if conditions for optimality. So why am I talking about this and why is this important? So this is important because many of the algorithms that are used to solve they are used to solve conic optimization problems. They are designed to attack these conditions. So they are designed to find points that satisfy these conditions. And typically a basic requirement for them to work is for you to have solutions that afford zero duality gap. So these lead us to the first example. But before that, let me just do a very quick review of semi-definite programming. So as I mentioned in the beginning, if we specialize our cone to the positive semi-definite matrix, we get what's called semi-definite programming. So I'm just writing this in a slightly different way. So here C and AI are symmetric matrices. This inner product is just the trace in a product. So it's just the sum of the component-wise products of these matrices. And this notation here indicates that a matrix is post-semi-definite. So just asking that the induced quadratic form is non-negative. Okay, so now that I got this review out of the way, let me show an example. So this is an example of an STP that has a positive duality gap. Why? Well, if we look at the dual problem, we have this entry here that is 0. Now, if you have a positive semi-definite matrix that a diagonal element is 0, this forces the elements on the same row and the same column to 0 as well. So the only way I can make this matrix positive semi-definite is if I let S to be 1. So the dual optimal value is -1. Now at the primal side, I have a similar issue. So one of the constraints is that the x11 entry, so the first diagonal element, is 0. So this forces the x12 and the x13 entries to be 0. So we have that the dual optimal value is -1, and the primal optimal value is 0. And we can see that none of the problems satisfy primal dual isolators because you cannot construct a matrix here that is positive definite. There are positive semi-definite matrices, but you cannot construct a matrix that is positive definite. So a question is, okay, so how bad is this? So let me show you something. Can you see my screen?
Yes.
Yes.
Yeah, so I'm trying to solve the problem I just showed to you via CVX pipe and using MoCaO. Oops. And it tells me that solver MoCaO failed. So yeah, so you couldn't get the optimal solution. So if you try to feed some problem that has a duality gap to a conic linear programming solver, chances are it won't work. It may even detect that something's wrong. So MoCaO detected that the problem is somehow ill-posed, but was not able to so it just fails. So typically, we want to enforce that we typically want to enforce that our problem is nice in a sense. We want to get rid of these kind of pathologies. So in this example, there are some specific things we can try to make things a little better. So one observation is that if we look at the dual problem, as I mentioned, we have this 0 here that forces S to be equal 1 and cancels out this part here. So one thing we could do is instead of solving this problem over the 3x3 positive semi-definite matrices, we solve over this smaller set here. So we consider the 3x3 matrices where the first 2x2 block is semi-definite and the rest is 0. So what happens if we do that? Now, this does not change, if we do this substitution, this does not change the set of feasible solutions, because the feasible solutions were already, the feasible matrices were already containing in this set to begin with. However, when we look at the corresponding primal problem, instead of having the original cone, it will appear the dual of this cone. Now, the dual of this cone, because we had zeros here, at the dual side, we have anything can go in these entries. So the dual of this cone will be the 3x3 matrices, such that the first 2x2 block, sorry, the upper left 2x2 block is semi-definite, and these entries here can be anything. Now, if we solve the primal problem over this cone, what happens is that we still have this constraint, but only this 2x2 block here is forced to be semi-definite. So the fact that this is 0 only forces the 1, 2 entry to be 0. It no longer forces the 1, 3 entry to be 0. So it's free to take the value -1. So in this way, now the optimal value of the primal problem is -1. And this closes the duality gap, right? So what happened here is that we replaced, at the dual side, we replaced the cone by a smaller one, but in such a way that this preserves the feasible region. So we are solving the exact same dual problem. But at the primal side, the cone changed to the dual of this one. So the feasible region of the primal side at the primal side expands. So this allows the possibility of obtaining a solution that closes the duality gap. Now, I think this is already appeared in the previous lecture. So in fact, this set is a face of the 3x3 semi-definite cone, and it has two key properties. The first is that it contains the feasible region of the dual side of the dual problem, and its latest condition is satisfied at this problem, because now the relative interior of this cone corresponds to the matrices for which this upper 2x2 block is positive definite. So you can take, for example, S equal 1 and T equal 2. So this will be 2, 1, 1, 1, 0, 0, 0, 0. And this will be a matrix in the relative interior of this cone. So now we satisfy its latest condition for the smaller cone. And this is essentially the basic idea behind facial reduction. So we have a problem that maybe will pose in some way. It doesn't satisfy its latest condition, and we identify some face for which the feasible region of, say, for example, the dual problem is the same, and then but its latest condition is satisfied. So then when we look at the other side of the problem, because latest condition is satisfied, the duality gap closes. Now, here I'm doing this from the dual side just because the notation is a bit easier on the dual side. But if I were interested in solving the primal problem, I could just do the same thing at the primal side. I could look at the primal problem, look at the primal feasible region, and identify some face that contains the feasible region and satisfy a constraint qualification like Slater's condition. Then, when I look at the corresponding dual problem, because the original problem satisfies Slater's, I will be able to close the duality gap. And this is the essence behind facial reduction. Are there any questions so far? if not, I'll continue a bit more. So before I talk about how facial reduction looks in general, I want to recall a bit about minimal faces. I think Vera has already talked about minimal faces before, but I think it's important to review a bit. So generally speaking, if I have C and K convex sets, and I have that C is containing K, I can always consider the minimal face of C containing in K. So this is the smallest, this is the minimal face of C with respect to K, which is the smallest face of K containing C. And we write like this. So how to obtain this? Well, there are several different ways. Here I'm just expressing the fact that the minimal face can be obtained by intersecting all faces that contain C. Now, because intersection of faces are faces, this will lead to a face. And it's possible to show that this indeed must be the smallest one that contains C. Now, the key property for us is that you can identify the minimal face via this property. So if you have C containing K, then the minimal face of K that contains C is a given face F, if and only if this face F just a moment. I think this should have been this. So if and only if this F contains if and only if this C is contained in F and their relative interiors intersect. So although initially we had like a cumbersome expression for we had a cumbersome expression for the minimal face. The way you can identify the minimal face is just finding some face that contains your set and such that the relative interiors intersect. Okay. So the basic idea for doing facial reduction is this. So now I'm working at the dual side, and I can do this without loss of generality because this is just how to say prime and dual notation. They are entirely symmetric. So if I have a conic linear problem, for example, in the dual format, and I want to solve this and try, but this problem has some issue like doesn't satisfy Slater's condition or something like that. What I can do is the following. I let this FD to be the feasible region. So it's these affine space. These affine space intersected with K. And I let F min D, I define F min D to be, so in a sense, I'm calling the minimal face of the problem D to be the minimal face of the cone K, the minimal face of the cone K that contains the feasible region of this problem. Now, one thing that happens is that how to say, if this minimal face is K, if and only if D satisfies Slater's condition. So in this case, the minimal face will be just K, and we are back to the original problem. But otherwise, this might be a smaller phase. And what we do is we replace K by this minimal phase. And then at the primal side, we consider the dual. Now, because of this key property that I mentioned, that when you have the minimal phase, it passes through the relative interior. This problem here always satisfies Slater's condition. So this problem, so the optimal value of this problem and these are always the same. So this is the essential idea behind phase reduction. Now, a question is, let me show again the same example I had before I move on. So this was the positive duality gap example that we had. Now, the feasible region of this problem, so the matrices that are feasible for this are the ones for which this part is 0. And because this part is 0, this can only happen if S is equal to 1. So are the matrices of this form. So are the matrices of where this 2x2 block is of this shape. And then the minimal phase will be like this. How do I know that this is the minimal phase? Well, because this phase here, first it contains the feasible region, and I have at least one point here that is in the relative interior of this phase. So if I take, for example, t equal 2, I have this matrix 1, 0, 0, 0. And this 2x2 block is positive definite. So this 2x2 block is positive definite, so it passes through the relative interior of this. It passes through the relative interior of this minimal phase. Sorry, of this phase. So I know that this is indeed the minimal phase. And then the dual of this is because here can be, because this part here is 0, when I take the dual of cone, it's just the 3x3 matrix for which this 2x2 block is positive indefinite, and this can be anything. Okay. So far, are there any questions? Or anything that was not particularly clear? Okay, so maybe I'll continue a bit more. So now, I guess a very reasonable question is, how can we actually compute the minimum phase? Because I guess for some problems, you can look at it and guess what is the minimum phase and try to check that your guess is correct by finding a relative interior point. But there is a more systematic way of finding the minimal phase, and which if it's a separating hyperplane theorem. So there is this slightly technical result that says that if you have a polyhedral set and K a convex set, and if you have that V does not pass through the relative interior of this set, if and only if I can find some hyperplane that separates them in such a way that this hyperplane does not contain K. So this is something that is very special about polyhedral sets. Whenever you have proper separation between a polyhedral and a convex set, you can always select the hyperplane in such a way that H does not contain K. And I'll show how this will be helpful for us. Now, so suppose that I have our problem in the dual format, and now because this is an affine space, so just a reminder that this is equal to this, because this is in a because is an affine space. Affine space. So to say that Slater's condition is not satisfied is the same thing as saying that this affine space does not pass through the relative interior of the cone. So this means, by the previous result, and since an affine space is polyhedral, that I can find a hyperplane that separates them in such a way that this hyperplane does not contain K. So this hyperplane will be given by a normal direction x and some constant. And the fact that, and I can assume without loss of generality, that the cone is above the hyperplane and the affine set is below the hyperplane. So this gives a set of inequalities that must be satisfied for all y in Rm and all z in K. Now, if we look at these two inequalities for some time, we will conclude a few things. So the first is, because this must hold for every z in K, it must in particularly hold for z equals 0. So this automatically gets us that this constant alpha must be less or equal than 0. And again, because this must hold for every z in K, x must be in fact in the dual cone, because if x is not in the dual cone, then you would have some z for which this is negative, right? So, and because you can multiply an element of the cone by a positive constant, I could consider things like x, m, z, where m is a large constant, and this would blow up to infinity. So there is no way that this part of inequality can hold, right? Because this is saying that this must be lower bounded by alpha. So this inequality forces that x is in the dual cone of K. And similarly, because I can take y to be equal to 0, we conclude that the inner product between x and c must be less or equal than 0. And for a very similar reason, it must happen that x is in the kernel of A, because if we consider this part of the expression, we have this. And if AX is different than 0, I can pick some y of large norm such that this will be positive and very large, and this would break this inequality. So the conclusion is that x must belong to the kernel of A. So this part of the inequality gives these two things, and the lower part of the inequality gives us these two conditions. Is this okay? Now, this will be the basic machinery for us to do facial reduction. So the idea is this. So if I have a conic problem in dual format, and I suppose that Slater's condition is not satisfied, by our previous discussion, there exists some x1 in the dual cone such that this holds. This inner product between C and x1 is negative, and x1 is in the kernel of A. Now, we consider two cases. If it happens that x1c is less than 0, then D must be infeasible. Why? Well, because if you had a feasible solution, to this problem, and so this is in K star, and this is in K. So this must be greater or equal than 0, because one is an element in the cone and the other is in the dual cone. But on the other hand, because I have this and this, the inner product, this implies that this is just equal to this is equal to Cx1, which is smaller than 0. So this is a contradiction. So if it happens that x1, this inner product is 0, then D must be infeasible. Otherwise, if this inner product is 0, then a very good thing happens. So X is in the kernel of A, so which is orthogonal to this, and is also orthogonal to C. So the hyperplane defined by X1 actually contains the feasible region. And because I'm assuming that H does not, I'm invoking this separation hyperplane that such that H does not contain K, then X1 is not orthogonal to K. Otherwise, the hyperplane K would be inside the hyperplane defined by X1. So FD is contained in this intersection, and this intersection is strictly smaller than K. So this defines a face. So X1, the hyperplane defined by the X1 is a supporting hyperplane to K. And when I take the intersection this with K, this becomes a face of K that is smaller than the original cone. I'll call this face F2. And then we repeat. Yes, this is just the observation I was making. So the hyperplane, the separating hyperplane theorem I'm using enforces that the hyperplane can contain K. And then I just play this game again. I have this new face F2, and I ask the same question. Is latest condition satisfied for this problem? If not, then I have an X2, that now X2 is in the dual of this face, and as before, we have these two conditions. And it's the exact same game. I have two cases. If it happens that this inner product is negative, then it must be the case that this is infeasible. Otherwise, if this inner product is 0, then this X2 is actually exposing some face of F2 that will be smaller than F2. So this containment here is strict. And now we define this face F3. And we play the same game again. We substitute F2 by F3 and ask whether this latest condition is satisfied. If it's not, we get a new vector like this, and we repeat. So this is the essence. This is the most basic form of facial reduction. I start with the original cone, and I ask whether its latest condition is satisfied. If it is, then we just say we're done. We found the minimal face. Otherwise, we invoke a separation theorem. And then there will be always two cases. One case we detect infeasibility, and in the other we find in a smaller face that contains the feasible region. And the small detail here is that in order to ensure that we actually are going to a smaller face, we need to invoke the correct separation theorem. And just going back to the same example that I showed, how would facial reduction look at this? So in this example, the facial reduction will stop in one step. So if I consider this X1 here, I can see that this X1 is orthogonal to first it belongs to the dual cone, because the positive definite cone is self-dual, so it's enough to pick another positive definite matrix. And this is orthogonal to both C. So in this case, C is this. So I can see that C x1 is 0. And also it's orthogonal to the matrix in the range of the underlying linear map. So we have something like 0, 0, minus t minus 1, and then we have minus s minus 1 minus 1. And this matrix is orthogonal to these two matrices. So this is indeed a valid direction in our sense. And then if you take the intersection of S3 plus with this, I'm asking that a matrix that belongs here, it must be such that the X33 entry is 0. So this means that X must be of this form, right? So this is precisely identifying that upper 2x2 block. So this is the facial reduction algorithm. The idea is that if the problem is feasible, the algorithm will construct a chain of faces. And I know this is correct, because whenever I am not at the minimal face, or whenever I do not satisfy its latest condition, I would most definitely be able to find a smaller face. And at the point where I cannot find a smaller face, it is because I found a face that satisfies latest condition. So facial reduction was originally defined by proposed by Ball and Wolkowitz for a more general class of problems, but there was some recent works like by Waki and Muramatsu. Pataki and his collaborators worked a lot on this, that discuss more specific versions of this for the case of conic linear programming. And the version I presented here is closer to the one that appears in this paper here by Waki and Muramatsu. So I guess this was the basic. This is the basic form of facial reduction that I wanted to talk about. And now, if I have time, I'm not sure. Maybe I have 10 minutes or so.
Yeah, 10 minutes is fine.
I wanted to go briefly through two applications, but before that, are there any questions? If not, let me continue a bit more. So one application of that I particularly like is connected to detecting feasibility. And I wanted to recall a result from linear programming, which is known as Farkas lemma. So Farkas lemma says that if you want, so similarly to proving that something is optimal, it's something hard, it's also non-trivial to prove that something is infeasible. Some problem does not have a solution. But in linear programming, what happens is that you can certify that a problem does not have a solution by obtaining a solution to another problem. So Farkas lemma says that if you want to convince someone that a given linear feasibility problem does not have a solution, it suffices to show a solution to another problem. And the way that these things goes is that one side is always easy. So this side is easy because if you have X like this, you just need to take the inner product between these two things. So one hand, because both are non-negative, this must be greater or equal than 0. On the other hand, because I have this and this is negative, so this is a contradiction. So the way the things works is that one side is always easy, and the other one is a bit more complicated. So, but the other one, it has a nice proof, the strong duality, like this. So if I let E to be the vector of all ones, I can build this problem, which is essentially I'm trying to minimize the inner product between C and X subject to these constraints. And then when I look at the dual problem, I get this problem, which is the original feasibility problem, but I have this displacement here. I have this special displacement here. So what happens is that when I add this displacement here, this problem is always feasible because E is this vector of all ones. I can always pick T to be a large negative number and make this feasible. And one interesting thing that will happen is that this will be the optimal value of this problem will be negative if and only if there is no solution. And this is not that hard to see because, well, if this were feasible, you could take T to be equal 0, right? So if you can find some Y for which this holds, I could take T equals 0. Now, if I invoke LP strong duality, so which always hold, provided I have feasibility, the fact that the optimal value is negative implies the existence of a primal optimal solution with the same value. And now, if I divide X star by minus the optimal value, I get exactly this. Maybe I went a bit too fast, but I hope more or less the idea is comprehensible. Now, I wanted to ask if someone can tell me what is the problem with this proof. So suppose that I want to do the same thing, but for semi-definite programming. So now I have some linear map for matrices, C are matrices, and this is a post-semi-definite constraint. And I want to know whether this statement is true, whether I can so as before, one side of this statement is always easy. So if I have an X like this, I just need to take the inner product. Now, because this is post-semi-definite and this is post-semi-definite, this is post-semi-definite, this is post-semi-definite, this is greater than 0. And now because I have this and this is negative, so this is a contradiction. So this is always true. So the tricky part is this one. But still I can give it a try. So I let I be the identity matrix. Now I'll be a bit more careful. And because I is the identity matrix, as before, if I let T to be negative, but with large absolute value, no matter, I can take even, we say Y equals 0, I can always find a big but negative T that will make this feasible. And because this is a positive definite matrix, I can also even have a positive definite matrix here. So this dual problem always satisfies latest condition. And as before, the optimal value of the dual problem is 0, if and only if this is feasible. Sorry, if and only if this is infeasible. Now, because D satisfies strong duality under this latest condition, I can do the same thing. So this optimal value is negative. So this will give a solution that has this optimal value. And I can divide the solution by minus theta D and get this X here. So does anyone want to take a guess? Where is the problem with this proof? maybe I'll just go ahead and say, so the part that doesn't go well is this part here. This part is not necessarily true. And this is one example of what can happen. So for example, if I have this 2x2 system where I ask this 2x2 tree to be this 2x2 matrix to be semi-definite, I cannot find, although this is infeasible, because this is 0 and this is 1, this cannot be semi-definite. However, I cannot find a matrix satisfying this because if I have a matrix satisfying these two constraints, this forces x11 to be 0 and x12 to be minus 0.5. So there is no certificate of this form attesting that this is infeasible. And the problem is that this problem has a special kind of infeasibility called weak infeasibility. So although this problem is infeasible in the sense that if I look at the underlying affine space, this does not intersect the interior, I can find points that are arbitrarily close to the cone. And this is essentially what makes it impossible to get a certificate like this. However, as we discussed, the facial reduction algorithm can detect infeasibility. So this leads to a certificate of infeasibility that you can always obtain just by using the directions that appear when you do facial reduction. And the idea is that if you give an infeasible problem to if you give an infeasible problem to the facial reduction algorithm, it will give us back a bunch of directions that eventually will certify that the problem is infeasible. And this proves that you have a generalization of Farkas lemma for general conic linear problems, but it's a bit more complicated using facial reduction. So these kind of ideas, I think, first appear in a paper by Ramana, and later there were similar ideas. So I think this was the first facial reduction algorithm that was able to detect infeasibility, and this was later also discussed by Pataki in quite detail. Now I have a quick example of how this certificate would look for this problem. So here is essentially the result of applying facial reduction to this problem and getting the direction. So I think I'll skip the computations later. I think this will be uploaded on YouTube. So maybe for those who are interested can check that indeed this works and shows that this problem is infeasible. So how am I doing with time? I guess I have no time.
Yeah, you can go over the example, I reckon.
So for the first direction is this is semi-definite. Now for the second direction must be searched in this space. So the space exposed, the face that is exposed by the first direction. So here we see that this x2 does not need to be semi-definite, because for this, the dual of this face is of this shape here. And at this point, I have that cx2, this inner product will be -1, and these together will show that this is infeasible. Okay, I guess I'll skip the last application I had. And if you are interested, there are several papers that that discuss some recent applications of facial reduction. I've worked more this on the theory side. So I work, for example, on using facial reduction to prove error bounds, and I'd like to advertise my co-author's talk. So Tim K. Pong has a nice talk where he talks about how facial reduction can be used to get error bounds. And I guess that is it. That's all I wanted to say for today.
Yeah, thank you, Bruno. Thank you for this amazing talk. So I would say we are opening up the floor for questions. Please just unmute yourself.
Sorry, maybe I can ask a question.
Yes, please.
Yes, sure.
Okay. So, Bruno, well, thank you very much. Really very interesting presentation, even for beginners. So my question is about that example about positive semi-definite matrices, but not positive definite. That's where the solver MoCaO failed.
Yeah.
So I just was wondering, so if something like that happens, do you have to come back to your problem and maybe reformulate it, or there is actually some software which would do it for you? So what is your recommendation in this case?
Well, so yes, actually nowadays there are some solvers. Sorry, there are some software that can help with that. So Pimenta and Parillo, they have a code in MATLAB to pre-process an STP, and it can get rid of some of these problems, right? So you can take a look at this paper, and also Zhu, Pataki, and Trondin, they have a software called Sieve STP that can process STPs and solve some of these issues. I forgot to show, but indeed, if you how to say, if you reformulate the problem over the smaller face, so over that 2x2 face, MoCaO no longer fails, and you are able to get the correct solution. That as I'm not sure if it's possible to see here, but MoCaO returns that S must be equal to 0.99999. Right. So there are quite a few possibilities. If you know your problem well, you can try to by hand find the minimal phase or analyze the properties, right? Or try some of the pre-processing software that these two, for example.
All right. Yeah. Thank you. Yeah. If you know the problem, it's also, to make it simple, I guess it's a good step. So, but if you just want to put all the burden on the software, yeah. Thank you.
I think there's something maybe I should say. One thing I should emphasize is that even a problem does not satisfy its latest condition, it doesn't mean it will fail. But you still have an advantage if you can do facial reduction, because you'll still be reformulating the problem over a smaller STP. So if you can do it, I think it's typically advantageous.
Yeah, thank you.
Other questions or comments, complaints? Okay, if not, let's thank Bruno again. And also at this point, I think I want to thank all the speakers. So our MoCaO lecturer, Vera, Isabel, who talked yesterday, and Bruno, that you participated and gave amazing talks. And clearly also for all the participants who sticked around until the last day today. Thank you, we had an amazing program.
Well, thank you very much for organizing also, Rai, Nadia, and Tom. So very well done, and I hope that I already look forward to next year.
Yeah, let's
attend the
see
next year's lecture.
what program is about next year. Alrighty, I think I stop